All right, everybody, welcome to another deep dive. And let me tell you, today's topic, it's a really cool one, even if I do say so myself.
I have to agree with you on that.
We're talking all about aircraft control surfaces, those often unseen but absolutely vital components that let those massive hunks of metal actually dance through the air.
Right. It's mind-blowing when you think about it.
It really is. I mean, we look at these planes, these enormous machines defying gravity, and it's easy to forget there's a whole lot of science behind how they actually move.
Yeah, most people probably don't realize it's not as simple as just turning a steering wheel,
Yeah,
right?
exactly. So to get us off the ground here, can you give us a quick overview of how these control surfaces actually work? What are the basic principles?
Absolutely. Imagine three lines running through a plane, almost like an invisible axis system. First, you've got one going from wingtip to wingtip, that's your lateral axis. Then nose to tail, which is your longitudinal axis. And finally, straight up and down, that's the vertical axis. And believe it or not, every single control surface helps the pilot rotate that plane around these axes.
So that's how they get the plane to do all those fancy maneuvers like pitching, rolling, and yawing.
You got it. So for example, the elevator, which is usually a separate surface on the tail or sometimes part of the tail itself, controls the pitch. That means pointing the nose up or down. Then you've got the ailerons on the wings, which control the roll tilting those wings back and forth. And lastly, the rudder, which is typically on that vertical tail fin, controls yaw, which is basically swinging the nose left or right.
Wow. So it's like a perfectly coordinated ballet with each control surface playing a specific part. But it's not just about these surfaces moving randomly, right? There's some serious science behind how they're actually interacting with the air to make the plane move, isn't there?
You're absolutely right. It's all about manipulating air pressure. Let's take pitching up, for instance. The pilot pulls back on the controls, the elevator tilts up, and that increases the downward force on the tail, which in turn lifts the nose up.
So even the slightest adjustment can make a huge difference in how the plane moves. Now, speaking of adjustments, let's talk about those flaps. They might not seem as impressive as, say, a giant rudder, but they're absolutely crucial, especially during takeoff and landing, wouldn't you say?
You're reading my mind. They might be subtle, but trust me, flaps are the unsung heroes of aviation.
So what's the deal with flaps? Why are they so important, especially during those critical takeoff and landing phases?
Think of it like this. You know how a bird extends its wings to create more drag and lift when it's coming in for a landing? Flaps do the same thing for airplanes. They're those hinged surfaces on the back of the wings, and they might seem small, but they dramatically increase the lift and drag.
Ah, so they basically give the plane that extra bit of oomph at low speeds.
Exactly. Without flaps, planes would need a much higher speed to maintain lift, which would make takeoffs and landings way longer, and probably a lot more nerve-wracking for everyone.
That makes a lot of sense. But our research mentions there are all sorts of different types of flaps, plain, slotted, Fowler. It's got me thinking it's not just a one-size-fits-all situation, is it?
You're absolutely right. It's not one size fits all. Just like planes themselves, flaps have evolved over time. Each type of flap has its own strengths, designed to meet the needs of different aircraft and flight phases.
So it's about finding the right flap for the right job. Okay, you've got me hooked. Let's break down these flap varieties. What kind of flaps are we talking about?
All right, well, let's start simple with the plain flap. Just like the name suggests, they're pretty basic. They just hinge down from the back of the wing. Basically, they increase the wing's camber or curvature, and that creates more lift, especially at those lower speeds.
Okay, so simple but effective. But I have a feeling there are some fancier options out there.
Oh, you bet. Next up, we have the slotted flap, which is probably the most common type you'll see. It's like the plain flap, but with a bit of a twist. They've got this gap or slot that opens up when the flap is deployed, and that allows air to flow through.
Interesting. What does that do exactly?
Well, that high-pressure air flowing through the slot actually gives the airflow over the flap a boost, helping it stick to the wing a bit better. What does that mean? More lift with less drag. A win-win for any pilot.
It's amazing how it all comes down to manipulating that airflow, isn't it? What other flap facts are you hiding up your sleeve?
Well, when you get to those larger aircraft, like the big jets you see at international airports, they use something called Fowler flaps. You could think of them like slotted flaps, but on steroids. Instead of just hinging down, Fowler flaps actually move back and down. This massively increases both the wing's curvature and its surface area.
So they're like the heavy lifters of the flap world, helping get those massive planes off the ground.
Exactly. They're crucial for those big jets, especially when it comes to reaching takeoff speed on shorter runways. They need all the lift they can get.
It's mind-blowing how much thought goes into something as seemingly simple as a flap. But these all sound like the more common types. What about those obscure designs I came across in the material? They really piqued my curiosity.
Ah, you must be talking about gouge flaps and zap flaps. Those names sound like they belong in a comic book, right?
Right, I know. What's the story there? Were they just experimental designs?
In a way, yes. Gouge flaps, while innovative, weren't quite as efficient as those Fowler flaps and were mainly used on Short Brothers aircraft. The zap flap, though, that one's really interesting. It was a unique design involving both sliding and hinging. But despite being pretty ingenious, it didn't see much commercial use. The most famous plane to use them was the Northrop P-61 Black Widow, a World War II night fighter.
Wow. So even in the world of flaps, there are those designs that, for one reason or another, just never quite take off.
Precisely. But it just goes to show you how much experimentation and innovation have gone into the field of aviation. People have been trying all sorts of things to make planes fly better.
Speaking of innovation, what about those Kruger flaps I read about? They almost sound futuristic.
They're pretty neat, actually. Kruger flaps are different because they're not on the trailing edge of the wing like the others. Instead, they're on the underside, near the leading edge. They deploy forward and down, which increases the wing's curvature even more. And they're especially useful on swept-wing aircraft, like the iconic Boeing 747.
Wait, so they're like flaps in reverse. Instead of hinging down from the back, they come out from the front. That's incredible.
It is. And then you've got the gurney flap. What's fascinating about these is how deceptively simple they are.
Oh, yeah. The gurney flaps. They do sound almost too good to be true, like a simple solution for a complex problem. Tell me more.
They're essentially small, fixed tabs on the trailing edge of the wing, and you often find them on helicopters. They're tiny, but they can really enhance the wing's performance. And the best part, they don't require a complete redesign.
It's amazing how such a small detail can make a difference. It seems like in aircraft design, every little thing matters. With all these different types of flaps, how do engineers decide which one to use? Is there a best type of flap?
You know, that's the thing. There isn't really a single best type. It all comes down to picking the right tool for the job. The best flap design for one plane might be completely wrong for another. It all depends on the specific aircraft, its size and weight, the shape of the wings, how fast it needs to go, even the airports it'll be using.
So there's a lot of factors to consider.
Oh, absolutely. It's a constant balancing act for these engineers. They need to find the perfect harmony between lift, drag, weight, and overall performance. It's a real testament to their ingenuity that we have such a wide variety of flaps, each one optimized for its own specific purpose.
It's incredible. We've come a long way from simple hinged surfaces to these amazing, almost futuristic designs. And speaking of the future, our research mentioned some really wild concepts like flexible flaps and morphing wings. Is that really something we might see in the future?
You're onto something. Imagine a wing that can literally change its shape in midair. That's the ultimate goal with these technologies. We're talking about using special adaptive materials that would allow the wing to morph and adapt to different flight conditions as needed. Potentially, this could lead to even quieter flights and even better fuel efficiency.
Wait a minute, so you're telling me that instead of having all those separate flap sections, the whole wing could change its shape? That sounds like something straight out of a sci-fi movie.
It does, doesn't it? But it's closer than you might think.
That is incredible. So what would be some of the biggest benefits of having a wing that can change shape in midair?
Well, for starters, think about fuel efficiency. We could see some significant improvements there, which means less of an environmental impact too. And that's not all. We could have quieter planes, smoother rides, even aircraft that can handle tough weather conditions better.
Wow, that's incredible. It sounds like we're standing on the edge of a whole new era in aviation.
We might be. And you know what? It all goes back to those fundamental principles we've been talking about. Understanding how airflow and control surfaces work together is key to making all of this possible.
That's what I love about these deep dives. You never know what you're going to learn. Who knew there was so much to discover about a seemingly simple thing like a flap?
It really highlights the incredible ingenuity that goes into every aspect of aircraft design, doesn't it? Every time we board a plane, we're benefiting from decades of research, experimentation, and those aha moments that lead to these groundbreaking innovations.
And speaking of aha moments, I think it's time we shifted gears and talked about another fascinating aspect of control surfaces that caught my eye: canards. remember seeing those in the research material.
Absolutely, especially in relation to that Grumman X-29 aircraft. What an amazing piece of engineering.
Right, with those forward-swept wings, so it
Oh,
looks like it's flown straight out of a science fiction movie.
it does, doesn't it? But before we dive into that, let's back up a little. What exactly is a canard, and how does it relate to those control surfaces? You're right, the X-29 is a perfect example of how canards can really shake things up in aircraft design. Basically, a canard is like a mini wing, but instead of being at the back like a regular tail, it's up front near the nose of the plane.
So picture a duck,
Yeah.
right? Hence the name canard. Okay, I'm picturing it, but what does this duck-billed mini-wing actually do?
It's all about control, specifically pitch control. Think of it like the elevator we talked about earlier, but with a twist. Since it's out front, the canard generates lift ahead of the plane's center of gravity.
Okay, I'm trying to visualize this. Why is that so important? I mean, how does that change things compared to a regular tail?
Great question. See, in a traditional setup, that horizontal stabilizer on the tail actually creates a downward force to balance the lift from the main wings. It's crucial for stability, but it also means the main wings have to work a little harder.
So they're kind of constantly fighting against that downward force in the tail.
That's exactly it. But with a canard, that lift up front changes the balance, and it allows those main wings to operate at a slightly lower angle to achieve the same speed.
So it's like the canard is giving the main wings a bit of a break, let them do their thing more efficiently. Would that then translate into fuel savings?
You got it. Less drag means better fuel efficiency, especially at higher speeds.
Hmm.
But going back to the X-29 and those forward-swept wings for a moment, they were really important because a canard setup can sometimes make the plane a bit unstable.
Really? That's interesting. I would have thought that having that extra lift up front would make things more stable, not less. So what's going on there?
It's a little counterintuitive, I know, but it all comes down to how the airflow behaves when a plane stalls. See, with regular aft-swept wings, the airflow separates in a way that actually helps the plane recover. But with forward-swept wings, like on the X-29, a stall can be more sudden and harder to control.
Okay, so those forward-swept wings weren't just for looks, they actually served a purpose. They helped counteract that instability caused by the canard.
Precisely. It was all about finding the right balance. And you have to remember, the X-29 wasn't designed for commercial flights or anything. It was all about pushing the limits of aircraft design, seeing what was possible, and it definitely achieved that. It proved that canards and forward-swept wings, while complex, could create a seriously maneuverable aircraft.
It's like something out of a fighter pilot's dream. And they were already experimenting with these ideas back in the 80s. It really makes you wonder what incredible advancements are coming next.
It really does. Speaking of advancements, remember those flexible flaps we touched on earlier?
Uh-huh.
Imagine the possibilities if you combine that technology with something like a canard configuration.
Whoa, hold on. A plane with a canard and morphing wings, now you're just showing off. But seriously, what could that actually achieve? What would be the holy grail of combining those technologies?
Imagine an aircraft that can just seamlessly adapt to any flight condition. Takeoff, high-speed cruising, landing it, could literally morph its shape to be perfectly optimized for each phase. We're talking about a total game changer for aviation, with massive implications for fuel efficiency, noise pollution, even the overall flight experience.
Okay, now you're getting me really excited about the future of aviation. It sounds like we're on the cusp of some seriously cool advancements. But for now, let's bring things back down to earth, literally, and talk about another fascinating aspect of aircraft design ground effect. It's not something we explicitly covered in our research, but I think it's worth exploring. Have you ever heard of ground effect? Ground effect. Honestly, not really. What is ground effect?
So ground effect is this pretty interesting aerodynamic thing that happens when a plane's flying really close to the ground, like during takeoff or when it's landing.
Okay, so those moments when you're right by the runway, just about to take off or touch down.
Exactly. At those super low altitudes, what happens is the ground actually interferes with the airflow around the plane's wings. It messes with those wingtip vortices, you know?
Wingtip vortices. Refresh my memory on those. What are they again?
You know how we talked about how planes generate lift? Well, one of the side effects of all that lift is the creation of those little swirling whirlpools of air that trail off the wingtips, like mini tornadoes almost.
Oh, right. Right. I've seen those before. Those swirling trails of condensation. Kind of cool looking when you see them. So the ground messes with those little tornadoes.
Yeah. When a plane's in ground effect, the ground basically stops those wingtip vortices from forming completely. And here's the thing. That reduction in the vortices, it actually reduces drag, which means the plane doesn't need as much power to stay up.
So it's like the ground's giving the plane a little boost, making it more efficient right when it needs it most.
You got it. And in fact, pilots actually use this to their advantage. During takeoff, they'll often fly close to the runway a bit longer, making the most of that reduced drag to gain speed and altitude before they climb higher.
That's really interesting. It's like a hidden advantage.
Mhm.
But how does this whole ground effect thing affect landing?
That's the thing. It's funny how something can be helpful and challenging. During landing, this ground effect can be a little tricky for pilots.
How so?
Think about it. You got a plane coming in for landing, it starts to descend, enters that ground effect zone, and boom, that extra lift from the ground effect kicks in. If the pilot isn't ready for it and doesn't adjust, the plane could end up floating down the runway longer than it should.
It's amazing how much pilots have to think about when they're landing a plane.
Oh, there's so much more to it than people realize. It really is a testament to the skill and precision it takes to safely land those big birds.
For sure. I've learned so much today. This deep dive has been fantastic. Thank you so much for joining us and sharing your expertise.
It's been a pleasure, really. Always fun to geek out about planes.
And to everyone listening, we hope you enjoyed this deep dive into the world of aircraft control surfaces. Next time you're at the airport or maybe see a plane up in the air, take a second, really look at it. Think about all those ailerons, rudders, those flaps, even that ground effect we just talked about. It's incredible how it all works together to make something so heavy, so big, actually fly. So until next time, keep those curious minds engaged. We'll see you on the next deep dive.